Hello all, good morning. This is Dr. S. Subbalakshmi, an assistant professor in the Department of Mathematics, SNS College of Technology. This is a case study on eigenvalues and eigenvectors in network stability. This is a case study with applications in electrical engineering. Introducing this thing, we will have the power system stability is very important or crucial for reliable operation. Dynamic models of electrical networks can be written in the matrix form. So power system stability is very important in reliable operations, and the dynamic models of the electrical networks is written in the matrix form. This is the basic introduction for the network stability analysis for eigenvalues and eigenvectors. Moving on to the next step. Eigenvalues of the system of matrices determine the stability. As we have discussed earlier, it determines the stability of the particular system. If the real part is less than 0, it is stable, and if the real part is greater than 0, it is unstable. So, real part means the imaginary part's opposite. So, in a particular value, if it is a complex number, we will say that the particular number to be a real part and a complex part, putting together as the complex number. Or oscillatory in nature if you have complex eigenvalues. So, if the real part is less than 0, we can name it as a stable system. If the real part is greater than 0, we will name it as an unstable system. And if the real part is equal to 0, we will say that the system is oscillatory in nature. And eigenvectors describe the modes, shapes, how different nodes of variables interact. So, how the things are interacting can be done using this eigenvectors. The interlinking concept behind the electrical systems of the network stability to the real world or to the eigenvalues and eigensystem is stated here. Interlinking concept, the electrical systems can be modeled using the state space equations. State space equations are nothing but the matrix equations, which is x vector is equal to a into x vector, where A is a system, which is a network, and which can be considered as a matrix here. Now, moving on to the mathematics concept. Eigenvalues of A determine the stability. Eigenvectors of A, which means it indicate the participation of the system of states. It indicates voltages, it indicates currents, it indicates generator angles. So, in practically, the meaning of this particular thing is if an eigenvalue has a positive real part, the network becomes unstable. As discussed earlier, we have the condition for the real part. If it is a positive real part, we will say that the system is unstable. We will consider a small problem relating to the network stability, small system stability. If the given matrix is like this, -2, -1, 3, -4, which is considered to be the system, what are the tasks to be done? We have to find the characteristic equation, we have to determine the eigenvalues, and we have to interpret the system stability using the real part of the eigenvalues. Moving on to the solution of the problem 1. The characteristic equation is determined using the formula determinant of A minus lambda into I, which is equal to 0. This is your characteristic equation, and this characteristic equation, on solving it, we will have the value of lambda to be minus 3 plus or minus I root 2. Minus 3 plus or minus I root 2. Interpreting, we will have interpretation on just manual looking onto it. We will have the real part to be minus 3, which means it is less than 0, therefore it is a stable system. And imaginary part is oscillatory but decaying, which means in the system is an imaginary part, we can say that it is decaying or getting reduced with the system stability. And on conclusion, what we can say is network is stable and oscillations die out over time. This is what we will conclude for this type of eigenvalues, which is lambda is equal to minus 3 plus or minus I root 2. For this particular eigenvalue, we can say that the system is stable and oscillations die out over time. Problem 2, which can be related to an unstable system. The given matrix is 1, 2, minus 3 and 4. The same tasks are to be found here, which is you have to frame the characteristic equation. You have to find the eigenvectors and comment on the stability. As usually, we have done the calculations regarding the characteristic equation, A minus lambda I is equal to 0, and on solving it, we have lambda is equal to 5 by 2 plus or minus I root 15 by 2. So, our real part is 5 by 2, which is 2.5. How about our interpretation here? The real part is positive, therefore we can say that the system is unstable. And the eigenvectors indicate the oscillation growth direction. Since it is coming under the imaginary number, we can say that it is oscillatory in direction. And on conclusion, what we can say, the network diverges and requires damping or controller design. Damping means we will just set a damping over the system, and our controller design we will have to make sure to control the system here. So this is what our interpretation is. Now, how to link the real world case study to the matrix eigenvalues. Stable eigenvalues indicate the steady grid frequency and voltage. Unstable eigenvalues indicates the power swings and blackouts. Engineers use these control mechanisms such as power system stabilizers, FACS devices, eigenvalue analysis in MATLAB and PSCAD. So these are the coding languages involved in eigenvalue analysis. So these things are steadily available over time to find the real world link between the eigenvalues and eigenvectors. And on concluding, the eigenvalue analysis is a core tool for evaluating network stability in electrical engineering. So as we have discussed earlier in a case study, we have got this network stability in electrical engineering. Now we have a small recap. In problem 1 we have stable oscillations, which means we have negative real part, and in problem 2 we have unstable oscillations, unstable growth, therefore we have positive real part. What are the key takeaways here? Eigenvalues are stability indicators and eigenvectors are participation factors. So this is how we learned the cases of network stability in using our eigenvalues and eigenvectors. This serves as a case study. Thank you.